In this video, we'll work on power spectral factorization of rational spectrum, and this is the only one we'll do in this course. We call a random process to have a rational spectrum if its power spectral density can be written as the ratio of two polynomials. Any Watson's stationary random process, you know that Sxx of omega shall be real and non-negative. Therefore, any power spectral density is a function of, can be written as a function of omega. So always this is a function of omega 2. In other words, it is symmetrical. So always Xxx of omega has this property. So is equal to Sxx of minus omega. So if you write it in Laplace domain, we said that omega 2 can be substituted by minus S2. So the power spectral density in Laplace domain can be written in this term. So zeros of minus S2 are the location for which this function is 0. And zeros of B minus S2 are those values of S in the complex domain. So this is, let's say, real part of S, and this is imaginary part of S. So for a number of points, A is 0. So we have zeros of A. For some other points, B is 0. So these set of points are called poles and zeros of Sx, because for the poles, this function becomes infinity, and for zeros of A, this function becomes 0. So for zeros of B, denominator is 0, so the function x becomes infinity. So a rational spectrum is if Si is a root. So if A of minus Si to the power of 2 is equal to 0, this function A is also 0 for minus Si. So A of minus Si to the power of 2 is equal to the previous and is equal to 0. So that means that in the S domain, if your function is 0 here, for this, let's say S1, it is also for 0. So if this is, you get S1 conjugate. So this should be, so this the roots are symmetrical, and therefore we shall be able to cut. So remember that power spectral factorization was just to write this one. So the correct one is to put a conjugate here and a conjugate here. So it's kind of more complete. Unless if you know that the coefficients of your filter are. So L of S must be stable, and thus the poles of L of S denoted by Si should have a negative real part. So the poles of S, which are zeros of B, are symmetrical. So if there is a pole on right side, there is another one on the left side. But because we want L of S to be stable, we get only the poles which have which are on the left side. So you should have this one. So, and also because L of S must be invertible, 1 over L of S also must have similar properties. So for zeros of that, so the real part of zeros and poles of L of S should be all on the left side of S-plane. So what we can do is to determine zeros and poles of Sxx, and zeros and poles, whatever happens on the left side happens also on the right side. So you have like a mirror for the poles and zeros, and the poles of L of S and zeros of L of S are these ones, and these ones are the poles and zeros of L of minus S. This is how we do spectral factorization. So what we do, we solve this equals 0, we solve this equals 0, we get zeros of A, we get zeros of B, and then we allocate the poles and zeros which are on the left side to L of S, and the one which are on the right side we allocate it to L of minus S. So we'll do a couple of examples. So L of S inherits all the roots and poles of H of S which have negative real part, which are on the left side of the complex plane. Such a filter is called a minimum phase filter. A minimum phase filter is a filter which is both causal and stable, and which has this one, which means that all the poles and zeros are having a negative real part.